continue with the lecture. If you remember, on Thursday we discussed the intersection of line segments. Now I will quickly go through the topics actually we have gone through and then try to finish this one in the first hour. If not, maybe at the beginning of the second hour, we will be done with line segment intersection. So as you see, we have many lines on the plane, and instead of actually doing a kind of a brute force approach, we prefer to use a much better algorithm. And for that purpose, we need to have a kind of an, let's say, a sweeping line, if you remember. And this is, as you see, the brute force algorithm is a time complexity of quadratic, but we will be using a much better algorithm that will be faster. And the thing is that it will depend, the time complexity of the new algorithm will depend on the number of intersection points. So we say that this is an output sensitive algorithm or intersection sensitive algorithm, which means that if you have no intersections on the plane, then in just a few, let's say, computation, you will come up with the solution and conclude that there is no intersection on the plane. But if you have some of the intersections, then your time consumption will be increased, and that's why we call these algorithms as intersection sensitive, or in general output sensitive algorithms. So what we were doing, if you remember, we decided to just check the line segments having some overlaps in the y-axis, and later we also conclude that that's not enough. Also, we should be doing some comparison on the y-axis, but this is how we started the algorithm, how we started the discussion. If you remember, we said that if you don't have such y overlaps, then you don't need to compare, for instance, this middle one and the upper one, since they do not overlap, their y intervals are not overlapping, so there is no need to do any check, to do any calculations. But you may do it with the first two since they have overlapped. And how we start the algorithm, we have an imaginary line, if you remember, at the top, and we move it downwards. And while this movement happens, we have some events. And at these events, we stop, do some computation, and then continue to the next event point. So in between the event points, we do no computation. So just the event points are important. And this is an example event point. This is the upper end point of a line. So which means that if you come up with an upper end point, and that means while going downwards, you come up with a new line. So you need to update some of your data structures and do more check. So the important thing is that during this movement, we should always be keeping the status of the data structures. For instance, right now at this point, we have 1, 2, 3, and 4 intersection with the imaginary line or the sweep line. So we need to keep the number of these or the name of these line segments in a data structure. Okay. And we said that this is not actually changing continuously. It just changes at the event point. So we can say that it's a discrete, let's say, operation. And at these event points, we are going to update the status data structure, and we need to do some computations and then go on with the next event point. So if it's an upper end point, new line is added to the status. So we need to check all these pairs in the status and tell whether there are any intersection with the line segments in the status or not. But if it's a lower end point, then that means one of the line segments is going to disappear from our status data structure. And if that's the case, then again, it's better we do some tests to check whether we have some intersections between the line segments. But we know that this is not enough, since that one will not be output sensitive. If you look at this bottom case, and if I simply draw a line and sweeping line here, for instance, we have many intersections with the sweeping line. But the thing is that the line segment here has no, let's say, communication or no interaction with the one on the left-hand side. So why do we need to check these pairs? We said that that's why we try to decrease this number of checks, since it's highly time consuming. It's better not do all the checks in the status. Instead, we do some checks with just the neighbors, not with the whole line segments in this status. We are going to just check the neighbors. This is actually the improvement we are going to make, and that will really decrease the time complexity. So that's why we are usually, we must order these line segments from left to right, which will define actually the X values. And then if you simply check the adjacent ones, then that will be enough. And we will prove that just checking the neighbors is enough to find all the intersections while we are going downwards with the sweeping line. For instance, here you see another event point. This is an intersection event point. The third one, the first one is upper end point. The second one is the lower end point. And the last event point is the intersection point. And why is an intersection? Since let's see here at this level, in our status data structure, the line segment, the order of line segments is J, and then L, then K, and then M, right? This is the order. But at the intersection point or after that intersection point, the order is updated. It's modified. Right now we have once again J as the first one, then comes K, L, and M. As you see, right now the order is modified. So that's why we call it as an event point, since some events happen there at that point, and we need to do some, again, check between the neighbors. So we have new neighbors. We don't need to check K and L once again, since they have been already checked. We need to do some check between J and K and also L and M. So we don't need to do check between J and M, since we know that we stated earlier that we only need to check the adjacent ones, not all the pairs in the status data structure. So these are the things we discussed. Yeah, this is a new event point. And our question was, can we find all the intersections by following such a scheme? Yes, we can find, but the thing is that we are assuming there is no horizontal line and there is no 3 segments or more which are meeting at the same event point. If these are satisfied, we can say that by following such a scheme with the sweeping line, we can find all the intersection points on the plane. So this actually summarizes our first lemma, a small theorem if you remember. So we have S and J. These are line segments I and SI and SJ. And we are assuming that they are non-horizontal. And another assumption is that they intersect in a single point P. This is P here. And these 2 line segments are intersecting. And another thing we are assuming is that there is no third segment passing through the same intersection point. And then we can say that in the upper region of P, we should have an event point where we check I and J together. Since they should have become adjacent, they should have become neighbors before this event point and should have been tested. So once your sweeping line is around here, this event point should have been completed earlier. Why is that? Since let's assume that our L is here, it's going downwards. This is an event point, right? An upper event point. So our data structure, status data structure will be I, just I. And since we have a single one, we can't do any check operations. We continue going downwards, and at that event point, what we have a new line introduction, and right now our status will be I and J, right? So since we have a new couple here, new neighbors, so we need to do some check. So once you do the check between I and J, then you should compute this point, this intersection point P. So this is actually the summary of first lemma, is stating that if you have two line segments which have an intersection point P, and this intersection point should have been computed before your sweeping line actually comes to that point. So this is the summary of first lemma, and an important lemma for the line segment intersection. Any questions, guys? Okay, let's continue. I think we were somehow around here. Let's summarize the algorithm up to now. We have a horizontal sweep line. This is going downward all the way. It stops at some event points. What are these event points? It might be the end point, or it might be the lower end point, upper end point and lower end point. These are the event points. And additionally, we have the third event point is the intersection. Since at these points, we need to do some computation. These are special points. And another issue is that in the algorithm, we should always order the sequence and order the actually line segments properly from left to right or from small x to larger x during this movement. And it should be always correct. It should be updated all the time. Otherwise, our algorithm will fail. So at event points, and we know that something changes, the order of the line segments and the status changes, and with the help of these changes, we need to do some computation, try to find the intersection points. This is the summary, and now we will be going into some details of the algorithm. So if the event is upper endpoint, then we know that it's a new segment introduction, and once you put that new segment into the status data structure, then you should be testing that new segment with the neighbors. So we have two neighbors for most of the time. If it's the left line segment, then we only have one. But if it's somewhere in between, then for sure we will always have two neighbors. And that means we need to be doing some checks for 2 times. And once we are doing these checks, we will obtain some intersection points. This is not the thing actually always happen, but at some neighbors, with the help of some neighbors, we may find the intersection point of these line segments below, as we discussed in the first lemma. So the intersection points below the sweep line are important. And if you find such an intersection, then what we are going to do actually, we will store that intersection point as an event point, and we need to store it to some kind of event data structure so that we don't have any problem and we will handle all these events. So here is the illustration. Before this point, actually, we don't have any events, right? Once our sweeping line is at that point, we have a new line introduction. New line segment is introduced into the plane, and this is Sj. Before Sj, what we have, I'm not going to, that's okay, Ijk, let's name this one as M, Sm, and this one as Sn, and this one as Sr, okay? Then what happens before, just before this one? Let me write the status. This is I, then K, then M, N, and we have nothing since R is a bit above. So this is the status of the line segment, sweeping line just before this event point. But once our sweeping line is at an event point, upper event point, what happens? We have a new line introduction, new line segment introduction, and our sweeping line will be I, J, K, M, and N, right? So this is now introduced. Since it has left and right neighbors, so we need to check whether we have an intersection between I and J. and whether we have an intersection between J and K. So during this intersection test between I and J, we can easily see that, yes, there is an intersection. You see, with the help of this checking operation, checking the neighbors, we found an intersection on this plane. So what we are going to do, we need to store this intersection point, let's say X intersection and Y intersection. We should be storing this intersection point to an, let's say, event data structure, since once we come to that intersection point, again, our status data structure will be flipped. The I and J will replace. So we need to do another check. That's why we need to always store them as event points and later do more checks with the new neighbors. Any questions about this operand point event, how we handle it? Okay. Yes, what happens when the event point is an intersection? We know simply that they will change their order, and once they change the order, then that means each one of them will have a new neighbor, unless it's the left or right end. Unless they're at the ends of the status, we need to again do some intersection tests between the new neighbors. And again, while we are going downwards, always the intersections below the sweep line are important, since the ones above the sweeping line have already been completed, so we don't need to actually worry about them. The intersection points below the sweeping line are still important. Yes, here is the example. This is an intersection event point, so that's why right now our sweeping line is halted, and at this point we need to do some computation. And just before, let's again name this one as A. These are all named, right? Okay. So just before the sweeping line, just before this intersection point, we have a status like A, J, K, right? And then L and M. But after this intersection point, things are modified. Right now, we will have L, K, and M. Okay. So the rule is that once we have an intersection event point, the order of these intersecting line segments will be modified, K and L, and they need to be tested with the new neighbors. So let's have a look at L. L should have been already tested with K, so we don't need to do any test with K. We are only going to test J and L. And another test should be performed between K and M, okay? So assume that if this one, let's say we have such a longer SK, and assume that this SM is coming such a way, so we might have an intersection point here. So at this event point, at this intersection event point, once you do check between SK and SM, you may have found this intersection point. As you see, this is an important point. You should always do checks between the new neighbors. If nothing changes, then you don't need to do any computation and continue to the next event point. But if the order changes in your status, then you should always do some checks. Any questions, guys, about this intersection event point? So what about the lower endpoint? It's again not that complicated. So once it's a lower endpoint, once our sweeping line is here, then that means this one will be removed from the status, and we will have one less number of segments in the status. Again, we will have new neighborhoods, so we need to do some check, but this time not to we will only be doing a single check. And again, if you come up with some intersection points below, again, they will be important for us. But they should be, this is important, this statement. Once you do the check intersection, and if you find that if they intersect below the sweeping line, then their intersection point is an event point. But this event point could have been detected already. So if you find an intersection point, but if it's already detected, then you don't need to store the same event point into your event data structure. Since that will be a duplication, you don't need to do that. And now I will show you this issue on this example. So we are now working on the lower endpoint event. This is the lower endpoint of SL. And as you see, after this event point, okay, or let me first write this portion. I'm just focusing on K and M. Initially, we have K, L, and M. And after this point, we'll just have K and M, right? Here you see we have new neighborhood according to the previous one. In the previous one, we have done computation between the check the intersections between L and M and K and L. But we haven't done any computation between K and M just above the sweeping line. This hasn't been done according to the point here. And now, right after the sweeping line, we have new neighborhood. So what we are going to do, we will do again a check test. And if you do the test between K and M, you will see that we have an intersection point above. Okay, sorry. Yes. So we have an intersection point here. Any comments on this? Is it an important intersection point? What do you think? Now, after the lower end point, we have a new neighborhood between K and M. We do the check whether they are intersecting or not, and we see that they are intersecting above the sweeping line. So what we should do? Should we store it into somewhere in some data structure? What do you think?
Hocam, shouldn't it have been found already before?
Yes, actually, this is what we are stating. We stated in the previous slide. Since we mentioned many times that the intersection points below the sweeping line are important. These are the important things. But as your friend said, this should have been computed earlier. Why is that? Since let's have a look at here. This is another event point. This is the upper event point. And once we have this upper event point, again, let's have this one is M, this is K, and let's say that this is R. And at this event point, what is our status? M, K, and R. And as you see, they are neighbors, so they should have been checked earlier. And once you do this check, you should have completed this intersection point. So you don't need to store it into the event data structure once you come here. But you need to do the computation. Since these two line segments might be intersecting at somewhere here. So you don't know the orientation. So regardless of your initial, let's say, computations, you should always do checks between the new neighborhoods. But the thing is that at that point, you do the check and you find that you have an intersection point above. So you have done the computation, but you don't need to store the event point, since that event point should already be in the data structure. This is actually the summary what we do in the lower event points, lower endpoints or lower event points. So we can say that now, with the help of this algorithm, once we swap the whole plane, we have completed all the intersection points. We shouldn't have missed any intersection points once you follow the details. Talha, you has a question. What we know about these lines? I don't visualize by code language. What do you mean by these lines? Which are, can you unmute yourself and ask it? What do you mean by these lines? Which are these lines? But Talha, I couldn't get your question. Okay, I think you don't want to talk. Okay. So you may post your question on Piazza and we can answer it later. Yes, now going into details of the algorithm, we did discuss some degenerate cases, if you remember. What were they? The first one was having a horizontal line segment, and the other one was having many line segments which are meeting at the same point. So if that's the case, then we should actually consider them as a single intersection point. Otherwise, you will have difficulties and you will output wrong number of, let's say, intersection points. Or you might have sometimes some overlapping, let's say, segments. This is again quite complicated. So that's why we'll ignore it for simplicity. Otherwise, since if two line segments are overlapping, then that means you have infinite number of intersections, and which is quite complicated. We will ignore it in our computation, in our algorithms. But for the first one, we can simply store it as a single intersection point. And for the horizontal ones, we will have a different solution. I think we will have a slide for it, so I don't need to discuss it right now. But it's better we discuss the data structures. So this is the algorithm, the fundamentals of the algorithm we have already studied. Now let's briefly focus on the data structure, what type of data structure we should use, and how we are going to store all these events and status, how we are going to keep our status updated while we are going downwards on the plane, and how the events are going to be stored. So let's focus first on the events. And if you remember in the previous slides, I always mentioned we should store these events into some structures. So can we store actually some of the events before we start the algorithm? What do you think? Do we know some of these events before we start the algorithm? Can anyone tell me, unmute yourself and just tell me, can we do that?
The starting points, the beginning points of the lines.
Yes, since they are inputs to the algorithm, we already know the upper endpoints and the lower endpoints. So before starting the computation, we can directly put them into our event data structure. And then the only remaining type of event will be the intersection points. And we will be adding these intersection points on the fly while we are going from top to bottom. But this will be the most complicated part of the event data structure. For events, we will be using an event queue. Why is that? Since the Y values are important, and we will be ordering them according to actually their Y values, and we will first handle the event having the highest Y value and then continue with the lower ones. So in that event data structure, we need to have some operations. What are these operations? We should be able to remove the next events, which is occurring from the queue event data structure, or queue type data structure. And it should be easier for us to remove it and then return it to the algorithm. Another issue is that I said that here the y values, they will be ordered according to y values, but what happens if they have the same y coordinate? Then the solution is not that complicated. We will always consider the one having the smallest or the smaller x coordinate. That will be the first one, and then the one having a higher x coordinate value will be the second one. So we can assume that instead of having a horizontal line, we will have a bit tilted line, so that we will always handle the first, actually the event point having the smallest x value. As you see, they have the same y coordinate, but once your sweeping line is tilted a little bit, this is very infinitesimal, very small value, and then that means we should be handling the event point having the smaller x coordinate. So in this Q data structure, on this event Q data structure, we should be able to insert some items on the fly, and these insertions may not be just to the top, to the bottom, but we'll be inserting some events somewhere in between the other values already inside the queue. Since the event points we are going to add are the intersection points, and as you know, the intersections might happen anywhere on the plane while we are moving our sweeping line downwards. Another issue, we might have coincident events. It might be an intersection and also a starting event point. If that's the case, then we should do some check and treat them as a single event. We shouldn't have multiple events having the same x and y coordinates. We should consider them as just a single event point. So that's why we need to do some check, do kind of a search in this event queue and try to find whether the corresponding event is already inside the queue or not. So to make it actually simpler for the implementation, we need to have a proper order. And what is that order? As you know, if you have some events, P and Q, assume that these are two event points, then we might have such an order. If P is smaller than Q, it's only true P has, let's say, a higher Y value than Q, which means that P will be handled first and then Q will be handled later. If you come up with a case that they have the same Y coordinate, this is the thing we discussed, then we will handle the one having the smaller x coordinate first and then the other one. This is actually the summary what we have discussed a moment ago. So with the help of this definition, with the help of this order, we will be putting all these events into our data structure. And for this type of queue, actually, we will be using a balanced binary tree. So does anyone know about things? What is a balanced binary tree, balanced binary search tree, or just balanced binary tree? So what we have in the binary trees, we always have, we can at maximum have 2 children, right? What do you think? Is this one a balanced binary tree? Obviously, this is a binary tree since we at most have 2 children for each node, but is it balanced or not? So why do you think it's not balanced? What is the requirement in the balanced binary tree? Let me make it like this. Any answers, guys? But this is getting complicated. So the thing is that in the balanced binary tree, we should only have one level difference between the leaves. So what are the leaves? These are all leaves, right? And we can at most have just one level difference between the leaves. If you have like this one, so this is another leaf. So if you have more than one level difference between the leaves, then we cannot say that it's a balanced tree, it's unbalanced, and we cannot use it in our application. Right now, for this problem, we need to use a balanced binary tree, and we will be storing our event points according to the defined rule, defined order we did in the previous slide. By using that rule, now we are going to store our events into this balanced binary search tree. So what we are going to do with each event point in our queue, let's say data structure, we will be storing the segments starting at that event point P. So once we have a kind of a value, let's say here, let's say that this is the event point P, and in that event point, we should be storing the segments which are starting with P. So we might have here, for instance, let's say L and M just. If their starting point is that event point, then we should be storing the information, or some pointers might be there. They should be pointing to the line segments which have upper end point as P. Another thing, we said that we need to do some checks while we are adding new items into this data structure. Since some of the events might already be in the data structure, and we don't want to have the same event point once again. So we need to do some search, or sometimes take one event point and then erase it. Since it's a search tree and binary search tree, we know that all these operations will take logarithmic time. So this is an advantageous thing. This is actually the reason why we are using such a binary search tree, balanced binary search tree. This will decrease the computation time, and most of the operations will be done in logarithmic time. And as you know, if you do some search operation, again, it will take the same computational time. That's actually the advantage of using a balanced binary search tree. Oops. Any questions, guys? Up to this point, after the data structure, the event data structure, we are using a queue data structure, and for that, we have a special balanced binary search tree. Now let's have a look at the second data structure we need to have, and this is the status data structure. And in that status, while we are discussing the details of the algorithm, we said that we should always be keeping, let's make it N, not L, obviously. We need to keep all these line segments in the status, and they should be ordered according to their X values, right? And what kind of data structure we need? Again, this is an important question. We should be properly storing this order sequence of segments which are intersecting our sweeping line. Since the order is wide order is important, since we are going to do some checks between the neighbors. If your order is not proper, then you will not be able to do these checks, and you might be losing time for the computations. And another thing is that this, again, status data structure should be dynamic. Since if you remember, at event points, we have some modifications. The order of the line segments might change. Some of them might be removed. We may have new line segments introduced into the status, so it should be dynamic. We should be able to do these, let's say, operations in a very short amount of time, and our actual data structure, the selected data structure, should have such capabilities. And again, for that purpose, we will use the same type of data structure, again, balanced binary search tree. And again, we will be storing the line segments actually which are intersecting the sweeping line as the leaves of the binary tree. So let me draw it here. If you have such a balanced binary tree, then the leaves actually will give us the order. Let's say this is R, M, and N. Then once you go from left to right, this should be giving you the order in the intersection with the sweeping line. So if you have such a binary tree, balanced binary search tree, then that means by simply looking at the leaves of that binary search tree, you can state that this is actually the order of line segments intersecting with the sweeping line, R, M, and N. This is how we are going to use this balanced binary search tree. And also we need to again have some kind of an, let's say, a rule so that we will be easily going to the leaves of the data structure. If you don't have a rule, then things will be complicated, or you will not be able to decrease the computation time. So for that purpose, we define a rule. This is very simple. We are always storing the segment. We are storing values into these actually nodes from the rightmost leaf in its left subtree. Okay, it might be complicated first, but I will show you an example, or I may focus on here. So right now, we have two internal nodes. This is the first internal node, and this is the second internal node. The other nodes are all leaves, right? So we don't need to store any information about the, let's say, rule, but for the internal nodes, we need to store some values. What are these values? And these values are determined according to this given rule here. So what it says that you should be storing a segment from the rightmost leaf in its left subtree. So let's focus on this topmost internal node. According to our rule, we should be storing the value of rightmost leaf from its left subtree. What is this left subtree of this node? Is here, this part. This is the left subtree. And what is the rightmost leaf here? Obviously, this is R. So I need to store R value into this internal node. Let's have a look at this one. Again, we should be finding its left subtree first. This part is left subtree. And since we have a single node, we can say that the rightmost leaf here is obviously M. Now our tree is complete. I can draw it once again here. This is N, M, this is M, this is R, and this is again R. And we constructed our binary search tree according to this rule. You should be always storing the segments, the value of the segments into the internal nodes according to this rule. What is that? You should be storing segment from the rightmost leaf in its left subtree. This was a very simple example, but in this next slide, we should have a more complicated case. Yes. So you see we have 5 line segments, and they are all intersecting with the sweeping line. And without using data structure, you can write it manually that the data structure or the status data structure should be in this order: I, J, K, L, and M, right? And if you look at this balanced binary search tree, you can see that while we go from left to right, I, J, K, L, and M, right? This is exactly what we have written here, I, J, K, L, M. So this is okay. But how we are storing these internal nodes? How we determine what to store into these internal nodes? It's according to our simple rule. What we do, we store the value. I think this one is more complicated. So let's have a look at the first one, the topmost internal nodes. So we are storing the rightmost leaf from its leftmost to left subtree. So this is left subtree of that internal node. And what is the rightmost leaf here? This is the rightmost leaf, right? Since it is SK, that's why we simply store SK into this internal node. For the other ones, things are simpler since they have just 2 leaves. This is our left subtree, and the rightmost leaf in that left subtree is SL. And again, if you look at here, this is left subtree, and the rightmost leaf is SJ. SJ is stored. This is left subtree, and SI is the rightmost leaf. So we simply store SI here. Any questions, guys, about this rule? It's a bit complicated, but fundamentally, we are only using this rule. We are storing the segments from the rightmost leaf in its left subtree. So this is the left subtree of the topmost internal nodes, and the rightmost leaf is SK. And that's why SK is stored here. Okay. As you see, we are using data structure, the balanced binary search data structure for the event and for the status, which means that we can perform most of the operations in logarithmic time. We can search for a value in the data structure, take it, erase it, it doesn't matter. So it will always take logarithmic time, and this is actually a nice feature of such data structures, and this will really decrease the overall time complexity of the line segment intersection problem. So let's have a look at the main algorithm in a pseudocode. So our algorithm is named as find intersections, and the input is a set of line segments in the plane. And obviously the output will be the intersection points in this line segments. So what we do, we need to have some data structures. The first one is an event queue. So we initialize it, and at first it's empty. And then what we do, as we discussed, we simply insert endpoints into this event queue. Since these are already known, we don't need to add these during the computation. We can do it at the beginning of the algorithm. And if the event point is an upper event point, again, we discussed it in the previous slides, we should be also storing the segments whose operand point is that corresponding point. And as a next step, we have another data structure. This is status data structure tau, and initially it will be empty, but once you start sweeping down the plane, we will be updating this status data structure. Yes, this is the Bentley-Altman problem. This is Bentley-Altman implementation. We didn't name it, but in the second project, as you know, we have a question regarding this line segment intersections, and this method actually we discussed is called as Bentley-Altman algorithm. And then what we do, we simply check our event queue. If the event queue is not empty, then what we do, we get the next event from the event queue, erase it, and handle that event point. So this is actually the summary of what we are going to do. But while handling these event points, we may be updating the queue data structure, since you may come up with new event points. What are they should be intersection points, and we need to be adding them into our Q data structure. But if they're not, if you do not find an intersection point, then you don't need to add new event. You will be done with corresponding events. So the most important part is the handling the event, how we are going to handle them. If it's an endpoint, then you may be inserting or deleting segments from the status data structure. And at the intersection points, we are simply changing the order of the segments in the status data structure. And during all these computations, during all these modifications on the status data structure, you should also do some intersection tests which have between the segments which have not been neighbors before these events. We also have some degenerate cases like multiple points or horizontal lines, but they are obviously a bit tricky. We're not going to discuss all these details. So for handling the event, we have such an pseudocode. So what we do here, we have an U of P set of actually segments whose upper endpoints is P. And these segments will be stored in the event point P in our Q data structure. And for the horizontal ones, if you remember, this is a degenerate case. You might have such horizontal segments, and their upper endpoints obviously defined by the left endpoints. So after you store all these segments, starting with the event point, upper event point P, then what you're going to do, you'll find all the segments which are stored in the tau, which is our status data structure, which have that event point P. So this is handling the event point. Once you come into this function, then that means you have an event point P. And now with the help of these statements, 6 statements, we are going to handle this event. And initially, we are storing a new variable. This variable is U of P. And in that variable, we are simply storing the line segments whose upper endpoint is P. And then what we do, we find the segments which are stored in our data structure, status data structure tau, which contain P, which is the handling event point. And they should be adjacents, they should be neighbors in the tau data structure. And then we have another variable this time. This is L of P, which is actually the subset of segments whose lower endpoints is P. So initially, we store the segments whose upper endpoint is P, and then we store the segments whose lower endpoints is P. So we have now U of P and L of P, and then we have another subset of segments, which is C of P. And this time, we store the segments who might have P in their interior, not as the upper or the lower endpoint. We may have some segments whose internal regions might be containing the event point P. So we have 3 subsets, U of P, L of P, and C of P. And then what we do, we have a union of all these subsets. And if this union contains more than one segment, if they have a single segment, we don't do an operation. But if they have, let's say, 2, for instance, let me use another pencil. So if you have such segments, assume that this is our handling point P, and this is another point. So we can say that C of P has 1 item, and U of P has 1 item. So they are containing more than 1 segment. They are containing 2 of these segments, okay? And then what we do, we report this P as an intersection point. And as you see in the example here, this obviously is an intersection point. And we also need to report these, let's say, subsets, L of P, U of P, and C of P. And then what we are going to do, we will be deleting the segments in L of P and C of P from our status data structure, but not the U of P. And then later what we do, we insert the segments in our union of U of P and C of P into the status data structure. Since this was a kind of an upper event point, if it's an upper event point, then we will be adding the line segment into our status data structure. If it's a lower endpoint, then we are simply removing it. But if it's an intersection point, then we need to report it. So now, yes, this is actually about the horizontal segment, but we are not going to discuss it since it's a bit tricky. And then we continue with the remaining operations. If the upper endpoint or upper, let's say, subset and the containing subset has no members, if the union of U of P and C of P is equal to an empty set, then what we do, we assign SL and R to be the left and the right neighbors of our event point, and then we call another function. Since if that's the case, then that means we need to do some intersection check. And this is done with the help of find new events function. This function is responsible for doing the checks between the neighbors. What are the neighbors? We have the event point already P, and L and R are the left and right neighbors. So if this union operation is not equal to an empty set, then what we do, we set a variable as S prime be the leftmost segment of this union operation in the tau data structure, and SL be the right, SL be the left neighbors of S prime. Again, we do more computation, the same type of computation for finding the intersection points with the help of this find new events algorithm. And then we have another variable as double prime as the rightmost part of the U of P union C of P, and SR is the right neighbor of S double prime in our tau data structure. And then what we call again the same function for the intersection tests. So in summary, I can say that this is doing what we discussed in the earlier slides. If it's an upper endpoint, that means we are adding a new item into our tau data structure. If it's a lower endpoint, we are removing. But if it's an intersection point, then what we do, we simply report that this is an intersection. But for the other ones, for the lower and upper endpoints, we do more computation, and these computations are summarized here. We simply check the neighbors whether they have a new intersection point underneath. Since the intersection points above the sweeping line have already been completed, we don't need to do more computation for them, but for the ones below the below the sweeping line are still important, so we should check them by the function find new events. And as you see in all of these, we have different cases. The inputs are a bit modified, but since we are handling the event point P, you should always keep P. You are checking the neighbors of P, but these main neighbors might be a bit different depending on the result of this union operation. Any questions, guys? So let's have a look at common intersection points. You see here that we have 7 of these line segments intersecting at a single event point. This is the intersection point, at the same time an upper endpoint and lower endpoint. So we have 3 types of event points at a single point. And this is here, and you can see the dramatical change between the status data structure. It's completely different. Just above the sweeping line, we have such an order. You see 7541, 7541, and then comes 3 and 8. Again, let's do the check our rules, how this value is written as S5 and how S1 is written here. We said that the internal nodes should be stored like this. We should be storing the rightmost leaf in the left subtree. So this is the left subtree of this node, and the rightmost leaf is S1. Okay, that's why S1 comes here and S5 comes here, and the rest is not complicated. But later, right after that complicated intersection point or event point, we have it simplified status. Right now, it's just intersecting with 5 of these line segments. 7, 3, 2, 1, 8. 7, 3, 1, 2, 1, 8, right? And again, the same rule. This is the left subtree of the topmost node, topmost internal node, and this is the rightmost leaf. So that's why S2 is here, and S3 should be here. Okay. And you see this is completely different. So while doing the computations between or right at this point, you need to be careful, especially while updating this tau data structure. If you have done something wrong, then probably in the below steps or below event points, you're going to have problems. Any questions regarding this complicated case? So what are, we know that computing the intersections are not that complicated. If you have the line segments, the ends, upper and lower endpoints, you can easily compute them. We do the test for all the neighbors. We come while we are going downwards, and we said that sometimes the intersections has already been maybe handled earlier. So this is the important point. While storing new event points into our event queue data structure, we should check it, and then we shouldn't have duplicate events in our data structure. So then now let's have a look at the most important, not the most important, but the second most important algorithm. This to find new event point is for checking these pairs. Now this is our event point. It's going to check whether we have an intersection with between SL and P or SR and P. So if these new line segments are intersecting below the line, below the sweeping line, or on the line, or to the right of the current event point P, then what we do, then that means the intersection point cannot be in the event data structure, so we should be inserting it into the event data structure. This is how we handle this computation, but the thing is that you should be doing some computation in this statement. In the if condition, you should be computing whether they are intersecting or not. Depending on the coordinate of the intersection, you should be adding the events or not into the event queue data structure. So what about the correctness of our algorithm? With the help of these algorithms, can we find all these intersection points? And yes, it's not that complicated. By using such fine intersection algorithms, we can compute all the intersection points on the plane between our line segments. And the next question is, the algorithm we actually develop as an output sensitive algorithm or not? What do you think? Obviously it should be, but can anyone tell me why it's an output sensitive algorithm? We started this journey to find an output sensitive algorithm. We come up with a one, but why this one is an output sensitive algorithm?
Teacher, is it because each intersection we are changing our, let's say, queue, and it's dependent in line segments? Also, in each intersection point, event point, we are doing some calculations, and because of that, both line segments and interactions are important. Then it creates an output sensitive algorithm.
Yep, that's somewhat correct. If you remember the pseudocode of the main algorithm, we started with actually inserting the event points into queue data structures. These were the upper and lower event points. So we don't need to do computation for the upper and lower event points, but we do computation for the intersection points. And as we know, the intersection points actually the outputs of this algorithm. So that's why we can say that in the pseudocode or the implementation, we will only be doing computation. We will only be spending time for the intersection points. For the other ones, for empty regions, we don't have extra computation. So that's why we can say that our approach is an output sensitive approach, and its time complexity shouldn't be quadratic. And here you see our running time is n plus L times the logarithm of n. And n is the number of segments we have in the plane, and L, I'm sorry, this should be I, not L, n plus I, and I is the number of intersections. So if you have less number of intersection, then our overall time complexity will be close to linear arithmetic. But if you have too many intersection points, if all the lines are intersecting with most of the lines on the segment, on the plane, I'm sorry, then we will be close to quadratic in time. But in reality, that's not the case. Only lines on this intersect with few of them. So we can say that this I value is not too much, it's lower than n, and depending on the case, we may simply ignore it. But finally, I can say that this is our overall time complexity, and it depends not only on the number of segments, but also on the number of intersection points. And this logarithm comes actually from the data structures we are using. We are using two main data structures, one for storing the events and the other one for storing the status. And for both of them, we are using a binary search tree. And we know that in the binary search operations, most of the operations are done in logarithmic time. Searching or finding an item, inserting, removing items always take logarithmic time. So that's why we multiply these operations with logarithm of n. Any questions, guys? So our main theorem is that once we have a set of n line segments on the plane, then their intersection in this set S will be computed in n times logarithm of n plus I times logarithm of n time. And for the space, we only need to store a memory of O of n. This is memory complexity. And obviously, I is the number of intersection points. So we can say that somehow this overall time complexity is linear arithmetic. So actually, this is the end of this chapter.